Hello, this is Kyle Davidson, and today I'm going to be giving an overview of the 89600B vector signal analysis software from Keysight, formerly ELINT, and specifically how to use it to understand radar signals, that is, gathering electronic intelligence on them, but less from an operational standpoint and more from the standpoint of providing you with a better conceptual understanding of how radar signals work and how it is we go about measuring them. Because I find in the class, and especially in a lot of the textbooks that approach this subject, it tends to be fairly mathy, to put it lightly. Especially when you start getting into details about frequencies of keying waveforms, Costas codes, noise radar, really any of the more advanced LPI, low probability intercept radar systems out there. You're looking at autocorrelation functions and ambiguity functions and pulse autocorrelation functions and so on. We really want to, from a practical standpoint, see the radar waveforms, see their characteristics, and learn to identify them. And that's what we're going to do today. And as you can see, running in front of me, I actually have a radar wave, and that's what we're interested in. So first thing we're going to do is a quick introduction to the VSA software, and then I'm going to run through 4 different waveforms. The first one's a linear frequency modulated pulse radar. The next one's some linear frequency modulation with some jittering of the pulse repetition frequency, and actually some changes in the pulse themselves. A Barker code, and finally an FSK radar. So, for your background information, I generated all these radar waves myself from a variety of sources, some were in MATLAB and some use System View. So first thing we'll do is actually go to File, Preset, and All. And we're starting from a blank sheet of paper. And that's what we have here, nothing. So we need to recall a signal first. And this software can be hooked up to run off a vector signal analyzer. And I do that myself fairly often. But we're just going to use a recorded data file. And the one we're going to use is this LFM radar signal. And we're looking at 2 plots of it right now. The top one is the spectrum domain. That is a frequency domain signal we're looking at. And the bottom one's time domain. And we can see those at the plot traces for trace A. Channel 1 is spectrum, and we have some choices there. And the bottom one down here is channel 1 main time. And we can look at different aspects of the signal right here, but there's some details we really need to look at first. On the main time one, you can see it's got a start and a stop time. And up here in the top, in the spectrum domain, we have frequency domain, we have a center frequency, because this is not recorded in the time domain. It's recorded after being downshifted from a specific frequency. In a lot of pieces of software, they will call this an envelope signal. Essentially, it's treated at baseband, but sort of tagged with the RF frequency, so we can see where it was recorded. In this case, it's 1 gigahertz. We can change that if we'd like by double-clicking. It's got a span of 36 megahertz, so the actual bandwidth it's recorded. And then it's got a length of time down here, and we can change the length of time we look at. Often it's shorter when we want to look at 1 pulse, and we want to see multiple pulses at the same time. We're going to increase the length there. And then the resolution bandwidth. And many of these things, as you'll see in a second, are tied together. So the first thing with the spectrum, we can change over here. If I left click and then scroll my mouse key up and down, I can actually see a bunch of stuff. I can change to a linear magnitude plot, real, imaginary, a phase of my spectrum, I in the Q, constellation, so on and so forth. But we are going to stick with the straight up old log magnitude plot. And we've got a few options even inside that. So you can see at the top here where my mouse is right now, I have 3 options. The first one is show digital persistence. And there it's going to maintain some history, so we can see the spectrum as it changes. We can show cumulative history. That is, it's going to maintain all the previous plots. And as we get more and more density at a specific area, it'll increase in color. And the last one is really important for any signal which is pulsed. And it shows spectrogram. And you can see what's happening there. I'm going to change the power level a little. It's got a dynamic range of 100 dB right now. But we just want to up that a little to bring out some of the color. Now it's from 0 dBm to minus 100. It was at 20 dBm to minus 80 before. I just did that by clicking and rolling my mouse button, my mouse wheel. So I'll pause to explain what's going on at this point. We still have the same signal we were seeing before in the frequency domain, and that's what's plotted along here at the bottom. And this may be more familiar from movies of old submarine sonar plots, but Hunt for October, for example. But this is actually a good way of analyzing our radar signal as well that's pulsed. So we have our frequency domain, and then the power is indicated by the color. So we would have a spectrum here centered around as it was before in the red, and then tapering off into the green, and eventually the blue is the bottom, and the noise here. And over on the left, on our y-axis, we have time domain. So we're seeing how the spectrum changes with time. Specifically, we're seeing our pulses, and we're seeing our pulse, since this is a linear frequency modulated pulse, being swept from a low frequency to a high frequency. And that's that slight diagonal twist, that nice diagonal line we have of our pulse right there. And then we obviously see a gap between the pulses, and that's where we are transmitting. So this really is an effective tool for seeing what is going on with your radar system. So we'll go back there, and we'll leave it paused for now, because down here in the bottom, I've paused it at the appropriate time, and we have a pulse right in the window, and we can see that pulse. We can measure that pulse. So we have the rising edge here, the trailing edge, and one of the most common things you want to do inside a radar system is you want to measure the pulse repetition interval and the pulse width. And I'll do that by clicking on that window. I right-click now, and I'm going to add a marker. And that was simply go to the plus symbol, add new marker, left click where I want it, and then I'm going to do it again, add another marker at the trail end of my pulse, and you can see them down here at the bottom, the markers window, where they are in the time domain and their magnitude. But I want to right click again, and marker 2 is highlighted. I'm going to change it from being a normal marker to a delta, and it's the delta from marker 1. So now down at the bottom I have marker 2 delta 1, and that is, it's telling us the difference in time between marker 1 and marker 2. And in this case it's 6.13194 microseconds, and that is our pulse width. That is the length of that pulse. Now I have a few other things I need to do to really characterize this pulse. And we're going to do that by going up here. We're going to go into click this button, go to a 2x2 grid. This simple drop-down menu lets me choose my arrangement of stuff, windows. We're going to go into main time, and we're going to add 2 main time little windows there. And we're going to change what I'm showing. The log magnitude is good to see where my pulse is and characterize some aspects of it. But I want to see the real part and the imaginary part, as well as I can look at the phase as well, the wrapped phase there. And in this case, we're actually going to go with the delay. And we'll start up here, and we're going to start by actually adding a second trace to this window. So I'm going to go right up to trace. I'm going to go with this plus symbol, add a second trace. We'll go to the drop-down menu, click main time again, and we want to see the imaginary portion. And if we click on this turn on overlay of this trace button here, and we do the same thing for this guy, we can see both the real and the imaginary parts of the time domain signal. And this is what the obvious signal we would expect for a linear frequency modulated pulse. Now, what we really want to do is characterize this pulse. And we can find out the center frequency straight from here. We can, if we go, we go over to this window. Sorry, we want to get rid of that marker. We're going to go show occupied bandwidth. And we get this little icon right here. And we can drag the marker over where we want at the center of our pulse. And then we can drag its 2 edges to show us the bandwidth, the power that's contained within these 2 bands to the left and right, our little gates here. If you go down to the bottom, we see trace A, marker 1. It's operating over 1 megahertz of, it's operating centered at 1 gigahertz and 990 kilohertz. And the power contained within that area is minus 3.4 dBm. And if we play it, you can see it changing with time as the pulse moves into the window and out. So really to analyze it from here, though, we run into the problem. I got lucky the previous time and paused it when the pulse was in the window, but we need to change that. And we have two ways to trigger in here. We have an input, and we go to trigger and playback trigger. Trigger is when we have this actually hooked up to an instrument and it is triggering off an input signal. We are on playback right now because we're working with a recorded signal. So we'll click on that and we can change it to magnitude. And we have a bunch of options. The level we're going to change it to trigger on is 100 millivolts. And we can go positive or negative slope, hold off style. And here essentially it lets us shift it left or right by minus or plus an amount of time in the time domain. So left to right of our trigger. And we can see that right there. It's our trigger levels on the time domain plot. It's triggered and we can see our pulse. So that's good. But, really the last thing we need to do to characterize this pulse is look at how it's swept over in the frequency domain. And right now we're looking at its delay, and the delay scale is a little off. We're going to change it to being 0.5 megahertz per division. And we can actually see now the signal, its rate of change in frequency. It's swept at 500 kilohertz per division, and it swept over roughly 6 divisions. If we wanted to, we could measure that with markers. Change our marker to a delta. And down here I'll actually clear these markers off. Yeah, we'll get rid of that guy as well. And we can see down here it traced D, marker 1 and marker 2, and marker 2, I'll pause it for a second, has swept over minus 2.994 megahertz. So the final thing we need to do, if we're really going to characterize this pulse, is really one of the most important, is to look at the pulse repetition frequency. And to do that, we need to go into our setup of the signal a little bit. And we see the measurement setup. We have our center frequency, and that won't change. Our span, we actually don't have, we can decrease it from here if we go down to 20 megahertz. And we'll get less frequency we're examining. But that's not really what we want. Usually we want to increase it. And to do that, we need to look at more frequency points. That is, we actually need to look at more of the time domain signal as well. So I've changed the frequency points down here from 801 to 25601. And I'll actually check the auto box at the same time. And if you note, our resolution bandwidth from 801 went from 100 kilohertz up here. When I go to, to 25601, it's at 3 kilohertz. So we get a lot more resolution. We're also going to change the window type because this is a radar signal. We're going to apply a uniform window, and you can crack open a DSP textbook if you'd like to see a little bit more about these. But radar signals generally don't have a window applied to them, so we're not going to apply a window to them when we analyze them. If we're doing a communication signal, it is going to be a little different. And I'll discuss that in my video on doing ELINT for communication signals. And the last thing we do over here is in the time domain, we can do some averaging if we want to. But in the time domain, we can change the main time length. And it's increased because we changed the number of frequency points we're looking at. But we can also look at the overlap of the signal. And I'll close this for a second and press play. I'll remove my trigger. change it to free one. And you can see it running, just like we would expect it to. And we can measure whatever information we'd want to. In this case, we're going to add a pulse. We'll get rid of the marker 1 and marker 2 over here. Idle markers. We'll add marker 1, and we want to just do the same thing we were doing before, but we're going to measure from pulse to pulse. We'll change marker 2 again to a delta, and we can see marker 2 delta 1 down here is 51 microseconds, and that would be our pulse repetition interval. And of course, the inverse of that would be the pulse repetition frequency. So if we do 1 divided by 51e6 and change that to a little minus, it works out to a PRF of just shy of 20 kilohertz. Pretty standard for a radar system. And we'll hide all the markers again. So back to going what we were talking about with the time. It was running relatively fast. And if I press play, you see that. It's visually hard to see what's going on. If I change this from 90 to 99, we've slowed it down drastically. And what we're doing here is we're changing the amount of information that the analyzer is taking in and throwing out every time it's analyzing the spectrum. And we've gone from throwing out 10% and taking in 10% to throwing out 1% and taking in 1%. And if we want to, we can also reduce the time spectrum, the amount of time we're examining in any interval. So we now have characterized everything we'd want from a linear frequency modulated signal, right? We've got the pulse repetition interval, we've got the pulse repetition frequency, we have the pulse width, we have the spectrum, its transmit frequency, we have its bandwidth. That was 3 megahertz. We know its modulation based on looking at the phase, and the delay is linear frequency modulated, and there is no jitter or anything applied to it. So that's a basic radar signal and how we can analyze it. Now, a slightly more complex one. Actually, so we want to recall a recording, and it's one I've made here. And you'll immediately notice something different about this. The spectrum itself doesn't look drastically different, but we're actually going to change this to show a slight digital. Actually, we'll go to the spectrogram. And what you're seeing here is 3 different pulses. So down, if we look at the main time trace B, you see there's a pulse here. It's a little shorter. This one's a little longer. And then we have a third one that is even longer. And we actually have a different separation between each of them as well. So I've jittered the pulse repetition frequency over 3 different PRFs. I have changed the pulse length for each one of the 3 pulses that it's swapping through. And I've actually changed the bandwidth of each pulse as well. These were generated at, I believe, 2, 3, and 4 megahertz. And looking over at the delay, we can see that. We can see this one, the first one, is swept over slightly less time. The second one is swept over a little more time. And the last one swept over the most amount of time. And in the spectrogram, we see a similar effect. And we'll change this down to like 20 microseconds. And there we can see the effects a little more. Our different pulses and their pulse widths and their different modulations. And here is where we would go in, and we'd actually be able to go in and look at the time domain signal. We'd measure, again, our PRF and our pulse width. We'd be able to measure the modulations. We'd see that each one of these is linear frequency modulated, but I have really messed with the PRF and the modulation for each one of them, really to throw some tricks at anyone who is trying to jam the signal or do any countermeasures of any kind. And if I want to, this is actually a good tip. If I want to save this, not just the recording, but if we want to save the setup, not as important for the radar signals because the setup doesn't take a ton of time. But if we're doing it for a really complex communication signal like an OFDM or radio to 11 or anything like that, setting up the analysis takes a fair bit of time. You often want to set up or recall just the setup, and we can actually do that for the signal. So we've got two more signals I want to show you, and the next one I'm going to recall is a Barker code. And we can actually see the Barker code right here. And this is a neat one to look at. It's slowed down a little, and I'm going to let the spectrum run for a little bit. And actually, oops, I'll get rid of that marker. We can see that sort of characteristic Barker code spectrum where you do have a significant peak right in the middle. But when we look at the pulse and the time domain down in the lower left, all we see down here is a standard envelope. But it really starts to come and show you what's going on when we see the phase and the delay and the stuff we wouldn't just get from a spectrum analyzer. And we need that phase characteristic to be able to analyze this signal. For the delay, in this case, we can see that the delay is sort of triggered where we get our bit changes. And Barker codes are a phase shift keying signal. They come in a variety of different number of bits, up to 13. And if you want to check out any of the books on radar, usually they cover these. But they have some unique characteristics because they limit time domain side lobes after you apply a match filter. So we want to look at the phase. And the wrapped phase down here is really what we want to see. So we can see our signal up top. We'll change it to the log magnitude. So inside the magnitude of that pulse, we see a bunch of bits. And we look at the phase. It's a phase shift keying, so it's just one phase or the other. And we see down here we've got, we'll call that a 0 since it's lower one, then a 1, then 2 zeros, and then a 1, and then a 0, and a 1. So this would have 1, 2, 3, 4, 5, 6, 7-bit Barker code. And if we want to do anything to characterize this signal, this is where we would now do it. We can find the pulse width, pulse repetition interval. We can see it's a 7-bit Barker code by examining its phase, and as well as its spectrum. And the spectrum of Barker code is very unique. It has that strong peak right in the middle that we're not used to seeing with a linear frequency modulated signal. Tends to be more flat across the top of its spectrum. And the last one I have is kind of neat. We'll go in here and it's an FSK signal. And get rid of that marker. There we go. I've waited for the spectrogram to show up, and we'll look at the rest of it in a second. But you can see from the spectrogram in the upper left, I have 3 specific frequencies it's transmitted on. And it's got 3 distinct frequencies. And you can clearly see it goes from lower to higher to highest. And we'll wait till it's in the window to pause instead of setting up a trigger. Actually, we'll change the length a little for the time to 50 microseconds. And just give it a second. There we go. And looking at it from a bunch of different perspectives, we can see some stuff going on. We'll look at the real part right here. We'll change the scale a little. There we go. And we can clearly see when we're looking at the real portion of the signal, we get a carrier, and it's modulating, sorry, not a carrier, but the baseband signal, and it's clearly modulated at a lower frequency. We can see in the middle portion, it goes to slightly higher frequency, and then finally to the highest frequency of all. And there's our frequency shift keying. We can look at its wrapped phase down here as well. We can look at its unwrapped phase if we wanted to. We look at its I and Q, and there we go. And the delay is, again, a neat way to see this. If we go and scale it up, the delay plot is actually, it's really, really handy for analyzing radar signals, because we can see frequency per division. We can see that it's changed at 2 divisions per, without even using our markers between each one of these signals. So we clearly get a shift by 1 megahertz for each frequency, and it's very clear that we can see it's perfectly flat at one frequency, immediately shifts up to another, and then finally shifts up to the last one. So we can easily characterize all 3 frequencies from our FSK signal. So that is my introduction to using the vector signal analysis software to do ELINT on a radar system. I hope you found it useful, and if you have any questions, please feel free to leave them in the comments.